It's early morning in the orthopedic operating room of the 3rd Hospital of Jinan in China's northern coastal province of Shandong. A busy day has begun. Preparations for surgery are underway. Liu Huashui is the director of the orthopedic department and lead surgeon for the coming operation. Lu Shidong, an experienced expert, will assist with and supervise the procedure. This is a special operation. Then there is a third, more unusual surgeon, an orthopedic surgery robot, to assist with the operation. The robot is unique. It is the only robot in the world that can perform an orthopedic operation on the limbs, pelvis, and spinal column. It's the 3rd generation medical assistance robot, a leading machine in its field globally. Some 1,000 kilometers west of Jinan, in the ancient city of Xi'an, another important surgical procedure is in progress. This is an operation to repair a damaged chest wall. Huang Lijun, thoracic surgery department director, will perform it. He would implant a piece of artificial bone. The artificial bone is made with remarkable new technology. The patient's chest was seriously injured in a car accident. Researchers have fabricated an artificial breastbone and rib section from polymer materials molded by a high-energy laser beam. The artificial bone was printed layer by layer, enabling it to be as complex and intricate as its natural equivalent. The artificial bone owes its existence to 3D printing technology that is now revolutionizing manufacturing. Meanwhile, in Xinxian County of the inland northern province of Shaanxi, Zhang Jie leaves his home for work. He works in a coal mine. He is the 3rd generation of coal workers, with his father and grandfather were coal workers. At 7:30 a.m., with his work clothes on, he rides an underground shuttle bus. Takes him half an hour to reach the coalface 100 meters underground. Were this an ordinary mine, he would soon be as black as coal. This is no ordinary mine, however. Zhang Ji steps into a control room and turns on the machine he will operate. A few dozen meters away, it comes to life with a roaring like thunder. The earth shakes, and soon it is plowing into the coal seam. The machine can mine 30,000 tons of coal a day, equal to the output of 1,000 traditionally equipped coal miners in a month. It can work non-stop in dark, humid, and dangerous underground tunnels. It is China's largest automated miner, the MG2662 intelligent coal mining machine. China, with a population of nearly 1.4 billion people, overtook the United States in car sales in 2009. It has since been the global industry's biggest market. China's car demand is expected to reach 30 million by 2020. Doing so didn't just require a giant industrial capacity, special equipment was needed too. At an automobile factory in the central city of Wuhan, a high-speed intelligence stamping system is operating day and night. Component inspector Yue Xuan is checking on the quality of its output. The intelligent stamping line can stamp 15 pieces of vehicle paneling per minute, making it possible for China to continue as the world's largest automobile producer. It is the world's leading high-speed intelligent stamping equipment. The world's leading orthopedic surgery robot. Cutting-edge 3D printing automated comprehensive coal mining machinery, and the world's most advanced intelligent stamping equipment. Intelligent manufacturing is creating infinite possibilities for China's future. In the orthopedic operating room in Jinan, the patient has been uninstated. Lin Huashui is checking a 3D X-ray scan to finalize the procedure's plan. Next to him, the surgery robot has been wrapped with sterilized film, ready to fulfill its mission.
The patient was injured in a car accident. Her whole pelvis was broken. A bone fragment is stuck in here, and if we don't deal with it properly, she'll become a cripple. After some discussion, we concluded that in this operation, the surgery robot can help to insert a screw.
In fact, 400 kilometers to the northwest in Beijing, similar operations have been performed countless times. Xu Jin, the research and development director of the orthopedic surgery robot, knows its every function.
The biggest challenges for doctors in minimally invasive operations are the limits of eyesight and the instability of hands.
No matter how skilled an orthopedic surgeon is, his vision can't penetrate human skin. To see the internal structure of bones and his hand movements can't be accurate to a level of micron.
In orthopedic operations, if a screw isn't accurately inserted and touches nerves or blood vessels, the patient may be paralyzed or even die. This kind of risk in operations has been unavoidable.
The orthopedic surgery robot, however, is not subject to human limitations. Its optical tracking cameras can see the bones under human skin and tissue. Its mechanical arm can perform surgery to a precision of 0.8 millimeters. Central processing system is like the brain that processes the information fed into it by the tracking cameras before directing its arm to perform surgery to a degree of accuracy that is beyond any human.
Imagine a black box with a pearl at the bottom. We need to send tweezers in through a hole in the top of the box to fetch the pearl. The robot is designed to assist the operator to see the scene inside the black box, to fix the position in real time, and to complete the task with a very steady arm. Only with these requirements can the task be carried out.
The surgery begins. Liu Huashui makes a small incision. After carefully consulting the scan, he sends the operation command. Will the orthopedic surgery robot conduct the operation accurately and successfully as expected? Xi'an's famous giant wild goose pagoda lies about 4 kilometers south of the old city walls. It was built over 300 years ago to house sacred scriptures. Its brick square pavilion structure makes it typical of the Tang dynasty. Today, with 3D printing technology, it's possible to replicate it in perfect miniature without picking up any bricks or tiles. "3D printing is also known as additive manufacturing. The means of manufacturing mainly include subtractive manufacturing, equal manufacturing, and additive manufacturing. Subtractive manufacturing means to bore, meal, and cut out parts so that original materials are reduced in size. Equal manufacturing means working on a piece of material over and over without subtracting or adding anything to it. Additive manufacturing, or 3D printing, works by eradicating a powdery metal or polymer material with laser beams to form molten pools of the material. These pools then solidify, and with the movement of the laser beam, they are added, quickly accumulating to fabricate the final object. It's called additive manufacturing because it creates objects by depositing a material, one layer on top of another.
Just like a bird builds its nest. If a bird is like a craftsman, the process of building a nest is a process of getting additional materials. Its speaker's like the 3D printing machine, and its nest is the final product. But we manufacture more complicated models than nests, and with better quality.
Li Bingheng, leading figure in the National Innovation Institute of Additive Manufacturing, has over 20 years' experience in 3D printing. For his team, printing a miniature of the giant wild goose pagoda is nothing more than a small trick. Now, with the help of biological 3D printing, their aim is to rebuild damaged bone in the human body. Every person is a unique individual who can't be replicated. But the human body is symmetrical. If we lose part of our bones in a car accident because of disease, can we replicate the missing portion from its mirror equivalent and implant it?
We can make an operation plan beforehand. We can restore the defective right side by copying the intact left side. With a 3D printing machine, we can print out an implant. The application of 3D printing to medicine will outmode traditional ways of treating patients and performing surgery.
The thoracic surgery proceeds well under the direction of Huang Lijuan. Before the operation, based on the CT image of the intact part of the patient's breastbone area, Lu Bingheng's team and Huang designed a 3D digital model for his artificial breastbone and rib section. When an artificial implant is made, a series of complex issues, such as materials to be used, toxicity, and rejection must be taken into account. For material, the surgeons, in this case, needed to research thoroughly to decide whether to use titanium alloy or a new polymer material.
Titanium alloy has better biocompatibility and fewer side effects, but in some cases, there can be problems. For example, if the skull is injured and we use the titanium alloy to mend it, metal has high heat conductivity and it's close to the scalp and is influenced greatly by outer temperature. In this case, the patient may feel his or her head is cold. That's not good. PEEK material, by contrast, is more like human bone. In terms of strength, it's even better than bone.
PEEK, short for polyether and ether ketone, is an organic thermoplastic polymer with a similar hardness to human bone and good biocompatibility. Huang Lijun has performed operations successfully with this material. Artificial bones made of PEEK material were printed out precisely and implanted into his patients' bodies.
In the past, it was very difficult to repair large chest wall defects. But in recent years, with the development of technology, especially 3D printing technology, we've seen its merits and applied it to the rebuilding of chest walls. With this powerful modern technology, we can now save more lives.
For Lu Bingheng's team, the joy felt on hearing the operation was a success has already given way to thoughts about their next step. In China, over 200 operations like this have been successfully performed. Their ambitions now lie in going further.
We will focus on biologically active tissue. The human body is one big piece of tissue with lots of holes. Liquids, like blood, and bodily fluids flow through it constantly. The next problem is to make sure 3D printed tissues can function normally in terms of bodily fluid flow and neuron growth.
One hot area today is how to manufacture biologically active organs, including artificial skin, cornea, and cardiac valves. It's a promising area. Regenerative medicine has made impressive progress. With 3D printing, it's now possible to produce biologically active organs, to research into genetic science. As a result, lifespan should be increased, with organs staying healthier longer.
Back in Shaanxi, Zhangzhai's intelligent mining machine is sharing off tons of coal underground. The provincial capital, Taiyuan, meanwhile, the factory that created it continues with development. The MG2660 intelligent coal mining machine is 16.9 meters long, 6.4 meters high, and it weighs 166 tons. 4 slipper legs rest on rails to move it back and forth. Each of 2 rocker arms raises and lowers a shearing roller, spinning at high speed to cut through the coal seam. To work intelligently, the first thing the machine must do is recognize a coal seam. Otherwise, rock will be shred along with coal, reducing its quality, damaging the equipment, and even hindering the normal operations of the mine. Recognizing a target object or material and tearing it apart from what is unwanted is a basic problem in artificial intelligence. In this case, how is it achieved? How to make the machine only dig coal and avoid rocks? Hao Shangqing is a senior engineer with over 30 years of experience. To tackle the problem, he has done research all around China and consulted many geologists and industry experts. In the end, he worked with China University of Mining and Technology to arrive at a solution. Use other methods to solve the coal mining problems. That is his plan. Seismic wave receivers are arranged in the tunnel, and seismic waves are used to detect where coal is located. Sensors attached to the machine's rocker arms recognize the different vibration frequencies of rock and coal. Then, with the help of an inertial navigation system, the machine can alter its positioning of the sharing rollers to avoid rock.
Detection with seismic waves is like a CT scanning of the coal seam. The sensors are like the human nervous system, and the inertial navigation system is the human visual system. When the intelligent mining machine works underground, it'll cut and collect coal and avoid rocks.
Spinning at high speed, the mining machine's rollers feature hardened metal claws with a weight of 12 tons each. The rocker arms must support this weight, so stability is a challenge. When the machine was first designed, the weight of its each rocker arms was 24 tons, which rose to 37 tons with the addition of a 13-ton sharing roller, since the 2 rollers move towards the same side. When the machine is working, it might lose balance and even overturn. Engineer Zhang Mingli redesigned both rocker arm and roller to reduce their weight. His calculations took into account the geological environment of the mine and the force-bearing conditions of the machine. Through data analysis, the combined weight was reduced to 35 tons. Finally, the structure was improved. The hardness of the metal increased, and the weight of the machine is now at a perfect standard. Stability has been achieved. Chang Zhenji, a technician in a machining workshop, is doing a tolerance test on the rocker-armed frame. This is a precision test that must be performed after the rocker arm frame is finished. Through an accurate testing of points, Lines and planes. Errors arising in the machining process are revealed. As he makes small adjustments, data on the smoothness and surface finish of the frame are being displayed on his computer to a level of microns. Development of the intelligent coal mining machine will continue. Engineers in China still have much work to do to make it more intelligent and powerful. In a car-making factory in the central Chinese city of Wuhan, a high-speed intelligent stamping system is working around the clock. Automobile manufacturing is normally made up of stamping, welding, painting, and assembling processes. The technology of stamping is considered the most important because over 70% of components are produced that way. A stamping line includes 4 multi-connecting rod press machines, a 2-armed feeding system, and an unstacker. To build it, essential technologies applied include a hydraulic and C-cushion, a simultaneous control system, an automatic mold changing system, and a whole line protection system. It represents the world's most advanced stamping technology. The stamping system itself is produced in Jinan. The factory that made it has a history of over 8 decades, meaning it has witnessed great changes in Chinese industry. Today, the factory is running smoothly, and Xing Yuji is spending the morning in the gear workshop. A graduate of the Shandong University of Technology, he started work in the factory 6 years ago. He operates 3 machine tools by himself. The large gears produced by these machine tools will be installed as core components of the stamping system at the heart of its work, turning out 15 automobile panels per minute. As usual, Xing logs into his computer with his personal data card. Technical drawings of gears and process are stored in the computer, and only he has the authority to see them. After retrieving the drawings, he sets the machine to operate. 6 years ago, when he started working at the factory, the setup was completely different. In those days, the first thing he did after arriving at work was to borrow the drawings from the design room. But very often when he arrived there, he would find other workers had already taken them. So he would have to go and look for them.
Now, we store drawings in the computer. With this information card, I can find the ones I want. In this way, the drawings will not be lost, leaked, or tampered with.
Now, all she needs to do is input a command, and the 3 machine tools will start to operate automatically. Paper drawings are a distant memory for him. At 10:30 a.m., 4 hulking metal shells are lined up in the welding workshop. They will be welded into the main beam of the stamping machine. 4 welding robots will complete the task. Each piece of precisely cut thick steel plate is tightly welded. Each welding joint is even and neat. Wang Yong is a senior technician. He has been welding for 30 years. Today, he doesn't need to wield a hot torch and sweat behind a heavy protective mask. Instead, no matter how delicate the task is, all he needs to do is to input a command, press on a remote control, and welding robots will do the rest.
In the past, we did the welding work manually. It was normal to burn our feet or hands, but now that rarely happens because robots replace us to complete the work. They are highly efficient. The work is finished with a better quality and nicer appearance.
In the afternoon, in a heavy processing workshop, a CNC planer type milling machine is about to change tasks. An intelligent automobile tool changer will change a tool bit. His mechanical arm picks up the new tool bit, which is a circular cut head, and passes it to the milling machine, before removing the old tool bit to precisely install its replacement. Then it deposits the old tool bit safely in a rock. Zhang Lei is an operating technician of the planer type milling machine with 13 years of experience. After the changing of the tool, he restarts the machine. For him, the biggest difference these days is that his uniform is always clean. In the past, human workers changed the tools. The tools were too heavy for Zhang to lift. With his hands only, so he had to use his chest and belly to assist. After completing the task, he was dirty all over. But now the intelligent automatic tool change will complete the tough task. Zhang Lei doesn't even need to go down to the factory floor. He can remain up above with tablet in hand. To input the required commands, the tool changing machine will then proceed by itself.
Now all I need to do is press the button and the tools will be changed precisely. It's much safer. We are also equipped with the tablet to consult the drawings. We don't need to climb ladders to fetch them.
Paperless gear workshops, intelligent automatic tool changes, and welding robots are all upgrading manufacturing. Manufacturing is becoming safer, more intelligent, and more efficient.
We don't just produce an intelligent stamping system and an automatic feeding system. The whole manufacturing process is paperless, intelligent, and automatic. It's in line with the call for smart technology in our country.
Elsewhere in Jinan, the pelvic fixation operation performed by Liu Huashui is underway. 3D scanning data of the area to be operated on is being fed in real time into a central processing system. The orthopedic surgery robot will carry out the operation following Liu's plan. Before the operation, the robot's mechanical arm tracker must be accurately calibrated. This is a positioning test. A 3-coordinate measuring instrument is used to test its positioning accuracy. Even in a state of deep anesthesia, a patient's breathing and heartbeat, as well as the doctor's operation, will cause their body to sway. Swaying, no matter how slight, make accuracy harder. The swaying, therefore, has to be factored in as the target site of the operation is tracked in real time. The central processing system uses the real-time data to control the robot's operating arm for saddle adjustments, to compensate for the patient's body sway, improving the accuracy of the surgery.
As a doctor, I know the limits of our hands and eyes, especially for bones and tissues in the deep area. The orthopedic robot helps us to complete complex operations in body areas where the human doctor can't see or touch.
The operation has reached a crucial moment. The robot directs its surgical tool to the required place and inserts a screw to a precisely predetermined depth from a precisely predetermined angle. Upon the lead surgeon's confirmation, the screw is fixed. Finally, the operation site is X-rayed again. Liu Xidong and Liu Huashui confirm that the screw's position is exactly as planned. The operation is a perfect success. The use of orthopedic surgery robots has turned orthopedic surgery, which was highly risky, into a scientific, quantitative, and controllable medical practice.
A 9-year-old child was brought to the hospital by his parents. They carried him in, holding him up by his collar. They said he had been to hospitals all around China, but none of them would treat him. Later, they found a hospital that could treat him. We were very happy. Finally found a hospital that would treat him. But there was a huge risk of dying. While talking, they let go of his collar by accident, and the boy fell down to the floor, like mud. We were scared, but the parents were quite calm, and they said he'd be all right. The whole family suffered a lot. In this case, during the operation, the robot pushed the screw to the predetermined spot according to our plan, and it was a huge success. At that moment, I felt really excited. I think intelligent technology is a capable helper of doctors, and it drives medical work from its second stage to a higher third stage.
In the National Innovation Institute of Additive Manufacturing in Xi'an, Lu Bingheng's team are working for their dreams. Meanwhile, thousands of miles away in Beihang University in Beijing, a team led by academician Wang Huaming is also working on printing complex metal structures. Inside its protective case, the nozzle of a 3D printer sprays out a powder of micron-sized ultrafine metal granule continuously and uniformly. A high-energy laser beam irradiates the powder, melting it instantly to form a liquid molten pool. After the laser moves on, the molten liquid solidifies quickly and forms successive layers. The layers pile up to fabricate the final object. Because of their large size and complex structure, some of the key parts of spacecraft can't be produced in the traditional way of welding separately made sections together. Doing so wastes a lot of materials and is time-consuming and very expensive. Moreover, each welding scene will be a weak point and a potential hazard for the spacecraft when subjected to high G forces.
It's very difficult to produce these large essential parts in a traditional way. Some technologies have almost reached their ceiling. Any further advance will cost a great deal. The loss outweighs the gains. So we need to change our approach, and things will become much easier.
An aircraft's landing gear is one of the most challenging pieces of equipment to make. When landing, the landing gear touches the ground first and has to bear an enormous impact. The performance of the gear is therefore critical to the safety of the entire aircraft. Manufactured in the traditional way, landing gear will be composed of dozens of assembled components. With the method of Wang Huaming's team, however, a large and complex metal part can be 3D printed as a whole. It will not suffer from structural weaknesses hidden within its equivalent part, made using the traditional method. During the 3D printing process, the metal powder melts instantly when it radiated with a high-energy laser. And just as important, when the laser moves on, the molten liquid solidifies at the speed of 10,000 degrees to 100,000 degrees. Through quick melting and solidification, the crystalline interior structure of the finished part turns out to be even with a better performance by all measures than parts made in the traditional way.
The key to this problem is to make it cool down and solidify quickly. It is a frontier technology in areas of both metal material and condensed matter physics.
Today, 3D printing technology has been widely applied in aviation, spaceflight, and military fields. It is used to provide key components for satellites, spacecraft, Mars probes, space stations, and aircraft carriers. At the National Innovation Institute of Additive Manufacturing, researchers continue to work on their terrestrial goals. Lu Bingheng, meanwhile, is thinking about how to get 3D printing technology to work beyond this in outer space.
We can do some work in the space station in outer space or on other planets if all the equipment or parts are worn out or damaged. What can we do? One way is to print them out on Earth and send them to space, which is very costly. Why not take a 3D printer into space? If the space station needs something, the printer can print out a component, and then the old one can be replaced. This way is more cost-effective. What's more, we could print out a giant solar power station in space by 3D printing and get lots of energy. Then we can transfer some production into space, making full use of space and energy there. All we need to do is send some powder materials into space, and we can print out high-speed trains and planes there and send them back to Earth. It'll save us lots of energy. And land.
Night falls in Taiyuan, Shaanxi Province. The assembly workshop for mining machinery is brightly lit. Zhang Wenjun, a technician, is testing the rocker arm of the intelligent coal mining machine. During operation, the rocker arm provides support and power to the sharing roller and drives it to rotate at high speed. Its bearing capacity and precision of movement will therefore directly affect the whole machine's performance. The 23-ton rocker arm is in place. Zhang Wenjun attaches sensors to its surface. Then he will apply mechanical pressure to test its bearing capacity. All indicators show that its bearing capacity is extraordinary and up to international standards. Equipped with smart eyes to recognize coal automatically and its powerful coal-sharing roller, the mining machine is, in fact, one of a team of 3 equipment systems needed to achieve a daily output of 30,000 tons of coal. The other 2 systems are a scraper conveyor and hydraulic support jacks. They are like 3 close brothers. While the intelligent miner digs coal, the scraper conveyor transports the coal, and the hydraulic support jack set up its working space to ensure digging and transporting proceeds safely and smoothly. In the control center, Jiang Jai is operating the mining machine. A sensing system perceives the spatial relationship between the 3 machines, controls their moving speed, and coordinates them to work in harmony. The intelligent mining machine has usurped traditional methods of coal production. As a 3rd-generation mine worker, Zhou Kai no longer needs to physically handle coal like his father and grandfather did. He only needs to operate the machine. In a clean and safe environment, science and technology are indeed turning our dreams into reality. At the stamping machine factory in Jinan, the beam installation work of an intelligent stamping machine is in progress. Afterwards, sparing and eccentric gear to power the machine will be installed in the beam cavity. Physical strength used to count in manufacturing. The power of modern machines comes instead from human ingenuity. Once the bearings and eccentric gear are securely in place, the installation of the machine's piping begins. The interval between the pipes, whether straight or curved, it's constant. And each curve has the same radian. The piping indeed is like a stave on which music flows, a symphony to the dedication of its creator. Xiao Tianfei, the piping installer, liked painting when he was a child. He entered competitions but failed to find success as an artist. 6 years ago, he graduated from technical college and became a pipeline assembler.
I feel painting and assembling are equivalent. Pipes on equipment. I like the lines and sketches. They are artistic. For me, my job and my interests are combined. My dream has come true.
It is not only the pipes installed by Xiao Tianfei that are perfect. All the fittings on the stamping machine are immaculate, as if the same master artisan installed them. Behind this industrial beauty are rigorous and international assembly standards. And because it meets these standards, the intelligent stamping line has won orders from top international automakers. This office is the design center of the factory, a concentration of its talent, wisdom, and imagination. Wu Yudong, a senior engineer, who participated in the creation of 8 stamping lines for the Ford Motor Company, still remembers the 8-year battle his team fought for a breakthrough.
The first stamping line we built for Ford was examined by a large group sent by them. A dozen foreign experts came here and asked us to disassemble the line for testing. When the 8th and 9th lines were examined, they only sent 2 Chinese engineers from the Asia branch for testing.
Outside, it's a sunny day. Wang Xiaohan is sitting in a bridge crane control box, 20 meters above the factory floor. When she looks down, the giant machines and workers look like scale models in a toy land. It's very funny. This is Wang's 4th year at the factory. Now 22 years old, she is training an apprentice. When operating the 300-ton bridge crane, she can lift equipment weighing hundreds of tons. Today, she is lifting the beam of a stamping machine. The beam has undergone all processing and installation procedures and will soon be shipped to a car factory to start its working life. In the car manufacturing plant in Wuhan, 5 large intelligent stamping lines are running at full speed. Ye Xuan's job as an inspector of parts will soon be taken over by a robot. His new role will be to be a good master. The servo line is the most noticeable among the 5 stamping lines. The word servo comes from the Latin word servus, meaning slave. The line is not only intelligent and efficient, 18 auto parts every minute, but also safe, controllable, and stable. The word servo therefore expresses the wisdom of humans in balancing technological progress with mastery of the world.
You don't necessarily see your competitors as enemies. Although we compete with each other, we also cooperate. If there isn't a powerful competitor, our desire to compete and our motive for improvement won't be strong. The quality of our products has increased in the past few years. It is competition that has boosted the development of technologies and the level of management.
Today, there are 9 intelligent stamping lines in total. The first 8 are operating at full capacity in 3 shifts. They make components for best-selling vehicles, including the Ford Raptor F-150, Transit, and Explorer. Other top international automakers ordering the system include Volkswagen, Nissan, and Volvo. This is truly win-win cooperation. From an orthopedic surgery robot that has revolutionized medicine in China to 3D printing that has broken through the ceilings of traditional manufacturing. From an intelligent mining machine that has outmoded old methods of digging for coal to a high-speed intelligent stamping line that has upgraded what it means to be made in China. All these marvelous achievements have their basis in ingenuity and innovation. In manufacturing, more and more intelligent production systems are becoming a reality. In factories, a new round of innovative research and development is underway. And on the streets, cars developed with 3D printing and manufactured by intelligent machines are improving both performance benchmarks and living standards. In China, the story of intelligent manufacturing has just begun.